Structure day 3. What are isotopes and how do we determine the average isotopic mass of an atom? Hit pause right now and please do the do not question. Okay, we're back. So we learned that whenever we see the symbol of the element Br, that's bromine, -80, the 80 represents the mass. We need to go to our periodic table and look at the atomic number. So when you go look it up, that's 35. So the question is, how many proton, electron, neutrons in the atom? Atoms are electrically neutral. So we have 35 protons, 35 electrons, because if it's neutral, it means it's the same, equal number. If you subtract them, you get 45 neutrons. Okay, let's move on. Isotopes. Isotopes are basically substances or elements that have, well, if you look at this picture up here, this is three substances. Well, these are lithium elements here, right? But what's the difference you notice here between them? Well, this lithium atom is a mass of 6, 7, 8. But what's the same about them? Well, what's the same is that they're the same atomic number. So what you need to know here is for isotopes, iso means something's the same, something's different. That they all have 3 protons. But when you subtract them, they have different number of neutrons because they have different masses. So very simple. Isotopes are elements that have the same protons but different neutrons. So look at the question below. In terms of subatomic particles, PEN. How do we know isotopes are the same and different? Well, PEN is short for proton, electron, neutron. So what did we just say? We said isotopes have the same protons different neutrons. Okay, let's move on. So here's an example, guys, right now of isotope of one element, hydrogen. If you notice, there are 3 isotopes of hydrogen. Isotope hydrogen with mass of 1, 2, and 3. And if you notice, they all have what? Well, they all have 1 as the atomic number or 1 proton. But when I subtract them, they have different number of neutrons. Okay, let's move on. Isotopic average mass. So today what we're going to do is we're going to find how do they calculate the mass number or atomic mass of an element that's found in the periodic table. Like, for example, how come carbon says 12.003? How come sodium Na says 22.9 something? Why is it not just 23? Well, we'll learn is that, what do we just say? We have more than one isotope of each one of those elements. So, here's a Regis question here, okay? Let's do this question. It's a part 2 question. First thing I want to do is answer question number 54. It says, determine total number of neutrons SI29. What do we say again? Whenever there's a dash here, the 29 goes on top. We need to look up the atomic number of silicon. So, hit pause and look up the atomic number of silicon in the periodic table. That's right, it's 14. So to get neutrons, remember we learned, right? That's what it wants. Once neutrons, simply subtract. You get 15 neutrons. Now, if you want to do the percent abundance here, okay, look at the question. It says find the correct numerical setup. That means, guys, it does not want the final answer. They just want you to show how you set up the answer. For calculating the atomic mass of SI. So we said over here, it's 27, so that's what you gotta do. You gotta do mass times percent abundance. So the mass here is 27.98. Times, well, what's your percent here? 92.22. Put it over 100. You can move back 2 spaces to the left, that's fine. But I like to put it over 100 so you don't make a mistake. Plus, well, if you notice there's 3 atomic masses here, so let's do the next one. 28.98. Times 4.69. Over 100. Are we done? No, there's one more. 29.97 times 3.09. That's a 0, I apologize. Over 100. And ladies and gentlemen, that is what's called the correct numerical setup. Because look, they did not ask for the final answer. They didn't say, and the calculated result. They just want that. Okay. Let's move on. Let's do this next question over here. It's another Regents question. All right. It says again, what does it say here? Show correct numerical setup for calculating atomic mass of sulfur this time. So all you need to do is very simple. You multiply the mass times percent abundance for each one and divide by 100 and then add them up at the end. So first calculation. If you like, you hit pause and do it yourself. Okay, we're back. 31.97 times 94.93 over 100 plus, you must put a plus there, people, 32.97. That's the next one, right? Times 0.76 over 100 plus 33.97. That's the next one down. Times 4.29 over 100 plus 35.97 times 0.02 over 100. Very good. That's it. That's the correct numerical setup. They did not ask you for the calculated result. If it did, then you know what to do. You multiply and divide by 100, add each one, and add them all up. Let's look at the question below here. Stay in terms of what now? Subatomic particles. That means we have to think of the what word there? Well, we have to think of the word pen. Pen. Pen is short for proton, electron, neutrons. One thing that's similar, what's different? So what's similar? We said same protons, different neutrons. And that's it.